Hello students, welcome to Dr. Saurabh sir classes. So in this particular video, as you know that in the previous video we have solved the question number 1a. So in this video we will be solving question number 1b. As you know, we are solving UPSC Maths paper 2 of 2021. Okay, so this is the second video for this particular solution of UPSC 2021 paper 2. So let's start with this question number 1b. So what is given? The test the uniform convergence of this series on the closed interval 0 1, right? So now, so here the partial sum it is given. So if we take this s on Sn x, that is the nth partial sum, so it is written as f1x plus f2x plus of fnx, right? So this is equal to, as we know, this is simply x to the power 4 plus x to the power 4 by 1 plus x to the power 4, 1 plus x to the power 4 whole square, 1 plus x to the power 4 whole cube, right, up to x to the power 4, 1 plus x to the power 4 to the power n minus 1. This will be the last term. Okay, so what is this nth partial sum? It will be x to the power 4 of 1 minus, this is 1 upon 1 plus x to the power 4 to the power n whole to the power n. So in the denominator it will be 1 minus 1 upon 1 plus x to the power 4, right? Now if we solve this further, so what it will be? So we will get, it will be 1 plus x to the power 4 minus 1 upon 1 plus x to the power 4 n minus 1. Okay, so this sum function with s of x. So now the sum function s of x, it is equal to limit n tends to infinity partial sum, the Snx. Okay, so it will be equal to 1 plus x to the power 4 for x not equal to 0, and it is equal to 0 for x equal to 0. Okay, so since the sum, you can see that, so the final answer is the, since the sum, here you can see that it is 0 at x equal to 0, right? So this sum function, that is Sx, is discontinuous at the point x equal to 0, which belongs to the closed interval 0 comma 1. So the given series is not uniformly convergent. Okay, on the closed interval 0 comma 1. So that is a very simple question, that is 1b. So this is not uniform convergence of the series, so this is not a uniform convergent series. Okay, so this is the answer of question 1b. So let us move to this next question, that is 1c. The question 1c is asking that if a function f is monotonic in the interval a comma b, then prove that f is Riemann integrable in the interval a comma b. So let us take this, let f be monotonically increasing, on the interval a comma b. Okay, so then we have this fa is less than equal to fx. Okay, so fx, the range of fx will be fa less than equal to fx less than equal to fb. That's interval it is given for all x belongs to the closed interval a comma b, right? Now f is bounded on the interval this a comma b. So then we have to find the infimum and supremum. So what is the infimum of f? It is f of a, and the supremum of f, it is f of b, right? So now let us take this eta is greater than 0 be given, and we write that p is equal to a, where a is equal to x0 comma x1 comma x2 up to xn equal to b, right? So this, what is this p? So b a partition, and where the partition in the interval a b such that del of r is less than eta by fb minus fa plus 1. Okay, for r is equal to 1 2 up to dot 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 up to n. Okay, now let us take this, the small r, this m of the small of the small mr and capital mr. So small mr, let us take this is the infimum, and capital mr, let us take this is the supremum of f. Okay, so this will be the supremum of f on the I of r is equal to x r minus 1 comma x r. Okay, since f is monotonically increasing, we have already considered, so the infimum of f r, so it will be f of x r minus 1, and the capital, that is the supremum of f, it will be mr f of x r, right? Now the u of pf minus the lower bound of this L of pf, p comma f. Okay, so p is the partition, and okay, so f is the function actually. So we are, so now this u of pf minus L of pf, so this is gonna equal to summation r equal to 1 to n. Okay, so it is mr minus small mr of delta r. Okay, so if we simplify this, it will be summation of n equal to 1 to n, r equal to 1 to n, sorry, so it is r this is r equal to 1 to n, this will be f of xr, or this is f is small and small letter, so f of xr minus f of x r minus 1, this of the del r. Okay, so this is, so del r we have already, this greater than is less than equal to this value we have. So this must be less than the integral this summation of r equal to 1 to n. So f of xr minus f of xr minus 1. Okay, so del r, you just put the value this eta by fb minus fa plus 1, right? So now what can we do with this? So if we take this, so it will be simply eta by fb minus fa plus 1 and summation of r equal to 1 upon n f of xr minus f of xr minus 1. So here it is equal to eta by fb minus fa plus 1. So this is equal to, then it will be summation, it is remove the summation, so f of xr, so it will be xn minus x0, right? If we put r equal to this n over here, so n ixn, and r equal to 1, so 1 minus 1 is 0. So f of xn and f of x0 we know what it is, so supremum of infimum of this, so it is nothing but fb minus fa plus 1. So f of xn is f of b minus f of a. Okay, so from here we can write this, so this is equal to, so fb minus of fa by the denominator, it is fb minus fa plus 1 of eta, it is less than eta itself. So for each this epsilon is greater than 0, there exists a partition P such that this u of p comma f minus l of p comma f is less than this epsilon. Okay, so this states that f is integrable on a comma b. So now what is the answer? Now this is for the case when f is monotonically increasing. Now for the case when f is monotonically decreasing in this interval a comma b, then we can prove that f is integrable also on a comma b. So hence the answer is f is monotonic on a comma b and also integrable on the interval a comma b. So that is the answer for this question number 1C. Okay, so thus we prove that f is a Riemann integral in this particular interval a b when f is monotonic function. So in the next lecture we will solve the last part of this question. I think there are two more parts, 1D and 1E. So we will solve it in the next videos. So see you in the next video.